Okay, so let us get started. So we spoke in the last class about some of the environmental influences on water levels. So we'll continue with that. So we spoke a little bit about gaining streams and losing streams, uh, and how they can impact uh, water levels in the area surrounding the stream, or just adjacent to the stream. Um, Now we'll talk a little bit about another impact that. Okay, Raish, can you put yourself on mute, please? Unmute if there's a question. Thank you. Okay, so now we will be looking at uh, another impact, which is that of how the impact of pumping translates in an aquifer and ends up affecting a nearby surface water body, let's say a stream. Okay, so under natural conditions, we have this setup that is shown here. I have a stream at one corner of the uh, this watershed, and I have a cross section of this watershed showing how the groundwater is moving towards the stream in the form of base flow. Right now, in this setup, suppose I introduce a pumping well which starts to extract some water from from the aquifer. What happens is, in the initial period, there is a change in the direction of the gradient. Previously, in the previous figure, that the one on the left, you see that the gradient is pointing, all the gradient is at every point inside this aquifer is pointing towards the river, right? It's all going towards the stream, right? Under natural conditions, this is what's happening. Now, when I introduce a pumping well into the system, I see that locally there is a change in the direction of the gradient, right? Locally, the gradient is pointing towards the well, and then away from the well towards the river, you still see water going into the stream, right? This is in the initial period after the pumping well starts to pump. This is what happens. Now, if this pumping well continues to pump, then you start seeing a lowering of the water levels. You can see that in the conceptual picture that is shown here. The water level starts to get even further lowered, and eventually, if you continue pumping beyond this time, then you start noticing that there is a complete reversal of the flow direction, even in the area adjacent to the stream, where you start seeing water actually flowing from the river into the aquifer, right? So this is a direct impact of uh, groundwater pumping on stream flow. So you can think of this as um, kind of an anthropogenic impact on nearby environmental the environmental flow. What is called environmental flow is this. How do you say this? So there is a notion in ecohydrology where people look at ecosystems and their dependence on hydrology. The notion is that of a minimum flow that is required for the surface water body to be able to sustain its services. When we say services of the surface water body, we are referring to the role played by the surface water body in helping some organisms survive. There's an aquatic ecosystem, right? There might be fish living in that stream or lake. There might be other living organisms. There may be some plants which depend on the river and so on and so forth. Now that is the ecosystem services provided by the river or by the lake. Now, when I have an anthropogenic impact in the form of a pumping well nearby, then it impacts the flow that is going into the river. So, if the pumping rate exceeds a certain amount, then as you can see in this last picture that you see on the bottom right, you actually see base flow has stopped, and in fact, we are getting flow to come into the aquifer from the surface water body. And if this continues for a sustained amount of time, then the surface water body may start to lose so much water that it's not able to perform the role that it is expected to perform, that of supporting aquatic life and so on and so forth, right? So those ecosystem services, uh, for the river to sustain its ecosystem services, it is supposed to have a minimum flow rate, which is referred to as the environmental flow. Okay, and this is an illustration of how groundwater pumping can actually hinder the surface water body from performing its ecosystem services. Okay, so this is one of the impacts of pumping on the groundwater body. Now, the important thing to keep in mind here in this situation is that the impact of this pumping on the surface water body depends on the nature of the aquifer, right? It depends on the properties of the aquifer, which determines how easily or how quickly the effect of pumping gets transmitted to the surface water body, right? Now, obviously, if in this case I have shown the well at a particular distance from the surface water body, correct? Suppose I move this well further away from the pumping from the stream, then obviously the impact of pumping. Suppose I move the well, but I keep the pumping rate the same, the impact that is felt on the surface water body will be delayed, right? Because it takes a longer time for the impact of pumping to reach uh, the boundary, which is where the surface water body is, right? So the distance of the pumping well from the surface water body is one of the factors that determines how much impact will be felt by the river, right? Obviously, that's one factor. The other factor is how much water I pump, right? This pumping rate that I'm maintaining and for how long I pump, right? So these two factors are also important. Number one, distance of the pumping well from the stream surface water body. Number two, the pumping rate that I'm pumping at, that also matters. And then the duration of pumping, how much time am I pumping? These three factors, these are external factors, right? The decision on where to place the well, how long to pump, how much to pump is independent of the aquifer. Then you get into the properties of the aquifer also, right? Different aquifers will behave differently when I pump the same amount of water at the same rate, at the same distance from a river. Different aquifers will have different responses. So there you have the impact of the aquifer properties, right? So here I don't know if we spoke about this earlier. There is this new parameter that we are going to introduce, which is called the hydraulic diffusivity D, which is simply denoted as the ratio of the transmissivity of the aquifer to the storage coefficient of the aquifer. Now, if it's a confined aquifer, it would be T by S, and if it's an unconfined aquifer, it would be T by SY, specific yield. Right? Now, depending on this magnitude of this hydraulic diffusivity D, the response of the aquifer differs, right? So the larger the value of D, the faster the impact of pumping or any stress on the aquifer propagates in the aquifer, right? So simply speaking, if D is larger, the effect of pumping will travel faster, right? And if D is smaller, then the effect of pumping will be felt at a slower rate, right? So which means now just by looking at the value of this diffusivity, if I have a confined aquifer, this S, capital S, is of the order of 10 power minus 3 or 10 power minus 4, right? Whereas if I have an unconfined aquifer, specific yield would be of the order of 10 power minus 1, right? So 0.1 or 0.2, which is about 10 power minus 1, right? So even if the transmissivity of a confined and an unconfined aquifer is identical, just by virtue of the storage coefficient of the confined aquifer being so low, right? So the denominator P by S, the denominator S is very, very low for a confined aquifer. It's 10 power minus 3 or 10 power minus 4, right? Just by virtue of that, the value of hydraulic diffusivity will be very high for a confined aquifer. For an unconfined aquifer, relatively speaking, the value of hydraulic diffusivity is much lower, which means that in a confined aquifer, if I pump water at a particular location, the impact of pumping will propagate very fast in the aquifer, right? In an unconfined aquifer, it will propagate relatively slowly, right? So that is the role played by this new parameter that I'm introducing here called hydraulic diffusivity. Okay, so the impacts both the timing and the rate at which the stream flow will get depleted, right? So this term stream flow depletion refers to, let me just go back, right? In this last figure, you start seeing stream flow getting sucked back into the aquifer because of this prolonged pumping, right? So now the stream flow used to have, previously, before pumping started, there used to be base flow coming into the, right? So this is base flow. Right? Now that base flow has been reversed to the point where I'm actually seeing the stream flow actually reversing back into the aquifer. So this process is called stream flow depletion, right? So now this hydraulic diffusivity actually impacts both the timing and the rate at which stream flow depletion happens, right? All other factors being the same, the hydraulic diffusivity plays a major role in deciding at what time the stream flow depletion happens and at what rate it happens. Okay, so I will, uh, uh, you know, there's the source that's given at the bottom of this slide is a very elaborate report. I urge all of you to read that report. Okay, I mean, you might not be able to understand every single thing that's mentioned in that report, but I would suggest that that is a very good resource material, especially if you want to understand the role of pumping on the impact of pumping on nearby surface water bodies. This is an essential reading for you to understand the different factors that play a role in this. Okay, so I'm going to give some illustrations of how this hydraulic diffusivity plays a role. Okay, so imagine I have a pumping well which is pumping at some constant rate, right? So it starts pumping at some time t at a constant rate, it just keeps pumping. Now, this is a qualitative chart, okay? It's not a quantitative chart. It's just to illustrate the role of diffusivity, the aquifer diffusivity, right? So here I have two curves. One corresponds to, everything else remains the same. The black curve corresponds to an aquifer with a large value of diffusivity, and the red curve corresponds to an aquifer with a relatively smaller value of diffusivity. So what is shown is the response at some distance from the pumping well, how fast the response will be qualitatively given a large value of diffusivity and a smaller value of diffusivity, right? So you can see that when the diffusivity is large, then the response due to pumping is very sharp, right? Very quickly the response is felt, and then you start to reach some kind of a steady state, right? Whereas if the diffusivity is smaller, the response is relatively slower. Okay, it takes a longer time for the aquifer to respond to this pumping rate. Okay, now please remember this is a qualitative chart. It is just to indicate how the different values of diffusivity can play a role in helping us understand how the aquifer will behave. Given everything else remaining the same, how the aquifer behaves, this is being illustrated here. Okay, all right. Now, one more example. Suppose I have cyclic pumping. Okay. Now, on the left, you see the pumping rate, it's kept steady and then it's brought down to zero. And then after some time, again, it goes up to the same pumping rate. It pumps for some time and comes back down to zero and so on, right? So I have some kind of a cyclic pumping behavior. Okay. Then again, you see how the response of the aquifer is, right? So the black line, remember, is for higher diffusivity and the red line is for lower diffusivity. And you start seeing how the aquifer responds and then recovers when the pumping stops. And then again, when the pumping resumes again there is a response, then there's a recovery. So you can see the cyclic nature of um, um, uh, the response of the aquifer on the basis of these different values of diffusivity. Now you can clearly see the larger the diffusivity, the more sharp the response is. The amplitude of the response is larger. Okay, when the diffusivity is smaller, the amplitude of response is relatively lower. So when the diffusivity is on the lower side, the aquifer is able to absorb these stresses without getting without showing very drastic changes in its response to the pumping rate. Okay, so this is again very qualitative description. So don't worry about, you just have to understand the role of diffusivity. Okay, it's not about remembering these curves or anything like that. This is, as I said, it's a qualitative response. It's not something that you need to memorize or anything like that. Okay. All right. Any questions? You'll have to unmute yourself if there's a question. Raish, can you please help out?
I have one question.
Go ahead.
Am I on?
Yes, yes.
Uh, we saw the second curve. It says response versus time. How are we measuring response? What is response? Is it the water level or drawdown? What is it?
Okay. Yeah. So let me just go back to the previous one. So it says response some distance from the applied stress. Okay. So the applied stress is the pumping well, and response, by response they're saying the, now here it would be drawdown, right? Otherwise it won't be increasing, right? If it's water level, it can't be increasing because of pumping. It has to be drawdown. Okay. Again, as I said, it's a qualitative figure. You can imply because it's increasing, that must mean that it must be drawdown, the decline in water level because of pumping. Okay.
Okay.
Yeah. Good. All right. So now I've given you a qualitative understanding of how the aquifer responds to different types of stresses. One was a steady stress, the other was a cyclic stress, and how the aquifer responds to these different values of hydraulic diffusivity. Okay. Now, if I were to actually, even before this slide, I might, well, anyway, okay, anyway, we are in this slide. Let's just look at this. Now, um, this curve tells, on the x-axis, I have the time since pumping started, and on the y-axis, I have the percentage of pumping rate. Okay. And there are two curves. One says water from storage, and the other says water from stream flow depletion. Okay. So just imagine what's going on. I have a pumping well which starts pumping at a particular point at a certain distance from a nearby stream. Okay. Now, initially, all the water that is being pumped by the well is coming from the storage in the aquifer. Okay, so that's why this water from storage curve, the curve that starts at 100 and starts to approach 0%, asymptotically starts to approach zero. It starts at zero, it starts at 100. At time t equal to 0, water from storage is at 100. Okay, which means initially all the water that I'm pumping out is coming from the storage in the aquifer. Okay, as time goes on, the portion that's coming from storage keeps decreasing, and eventually it reaches zero. Simultaneously, this other curve keeps increasing. What is that other curve? It is the water coming from stream flow depletion, right? At time t equal to 0, there was zero stream flow depletion, right? Because there was no pumping before the pump was placed and started pumping. Therefore, there was no stream flow depletion. Once I start pumping, I start to see more and more stream flow depletion. And eventually, when you reach steady state, all the water is coming from stream flow depletion, and none of the water is coming from storage in the aquifer. Okay, so this is an indication of where the water is coming from to that particular well. Okay, and there are two times that are marked on the top of the x-axis. One says storage dominated supply, that is until storage is 50% or more of the total pumping, and depletion dominated supply is the time after water from stream flow depletion exceeds 50%, right? So this point at which 50% is coming from storage and 50% is coming from stream flow depletion, once you cross that time, then you have depletion dominated supply, and before that you have storage dominated supply. Okay, this is a very important qualitative curve for you to understand, right? Because this is a fundamental aspect that a lot of uh, you know planners for of groundwater resources they don't take this into account, right? It is ignored this fact that for initial time, all the water is coming from storage, and then later on, whatever pumping is happening, the water that is coming out of the pumping well is basically water that is being lost by some stream or some lake nearby, which is losing that water. It could be even more than one stream or more than one lake. They could be supplying the water to this pumping well, right? In fact, in the first project, a lot of you, there were a couple of papers that kind of referred to this idea. One was the water budget myth, and then the other was, I think it was why hydrogeologist model or something like that. I don't remember the second paper, but two papers that two of the groups worked on were explicitly spoke about this idea at a great length. Okay. Anyway, so this conceptual picture is very important for you to understand that stream flow depletion is the major source of pumping. All the water that is being pumped is coming out because some stream somewhere is getting depleted. Now, which is why if you look at South India, the vast majority of rivers in South India do not flow throughout the year. This is a recent phenomenon. This is something that has happened in the last 40, 50, 60 years. Ever since the tube well technology has come into India, come into the world, come into India, as farmers started pumping water for their irrigation, what would happen initially? It would come from storage. The water would come from storage, and as time passed, the base flow that used to be feeding our rivers throughout the year, that started to get depleted. Okay, and then the stream started providing water uh, to the to the aquifer, right? So therefore, the reason you will see that in southern India, when you cross a bridge, right, and if you just look over the bridge, majority of the time you will not see any water. You might see some sewage water because there might be a city nearby, but that's not the original water of the river, right? But if you go to any other portion of the stream which is not near a city, you will see that the river bed is completely dry unless there's been a rainfall event recent in the recent past. Okay, most of the time the river beds are completely dry, and that is because of this stream flow depletion that is happening. And this, as I said, is a recent phenomenon. This excessive groundwater pumping is something that has been taking place only about in the last 60, 70, 80 years. Okay. And of course, tube well technology has become more and more prevalent since the 1980s in India. Okay. Before that, uh, there were no people used to drill some shallow wells and maybe take out a little bit of water, and electricity was not so available everywhere, so that it was very difficult to pump a lot of water. But now, with electricity becoming available in all the villages all over the country, and with tube well technology improving, drilling technology, all of that improving, we have been able to, every farmer has got a well basically. Okay, and they have free electricity, so they pump a lot of water, and that is the reason why you will see there's a significant amount of stream flow depletion, particularly in the southern part of India. In the northern part of India, it's still there, but generally speaking, you have the you know, these perennial rivers, which of course also benefit from you know, some glacial snow melt and so on, but they are also sustained by you know, what I'll just call they're also sustained by base flow. So in general, this is the reason why you start seeing rivers going dry. Okay, which is because of the major groundwater consumption that is happening across the country, not just South India, all over the country. Okay, and in fact, the fact that India now has food security, right? You will see every year the agriculture minister, whoever the agriculture minister is, stands up in parliament and says, India has produced record food grains this year. Okay. Every year they break the previous year's record, and it's happening. So it's something that, you know, that has solved India's problem, you know, of a lack of food security. So if you went back 60, 70, 80 years back, right, India did not produce enough food grains. And then the Green Revolution happened, and then groundwater has played a major role in ensuring that India has food security. But it has come at the cost of our rivers being completely cut off from getting any base flow, which is why a lot of rivers in South India are all dry except when there's a rainfall event. Okay. Any questions? And there might be lots of questions on this. I don't know. Let's see. Any questions?
Yes, sir.
Go ahead.
So from the
Your voice is breaking. Can slow down, slow down. Maybe come closer to the podium where the microphone thing is. Go ahead. Sorry, I can't hear you. Huh, now it's better. Go ahead, go ahead. Can't hear, can't hear. Why don't you quickly type into the Aish, can you just type his question into the chat box? Briefly.
So in
Sorry, Shantanu, I really can't hear you. Yeah, why don't you come closer to the podium and can you repeat his question, Raish? I can't. Sorry, Shantanu, why don't you type in the chat box, please, quickly?
chat, I joined
Quickly. Yeah, this is a problem. Raish, we have to fix this microphone issue.
Yes, sir.
Yeah, now I can hear clearly. I think when you get closer to the receiver there, it's better.
So, sir.
Why can't somebody type the question in the chat, huh?
Am I audible, sir?
Yeah, now I can hear you. Go ahead.
Okay, okay. Sir, from the graph we observe there, one second. Water from stream flow depletion is increased with respect to time, and water from storage is decreased with respect to time. From
Correct.
the storage is a function of inflow minus outflow. Whenever from the outflow, storage dominated supply is less, depletion dominated supply is more. That means two situations may be arises. If inflow is greater than outflow, then storage is positive.
No, no, no. Wait, wait, wait. Yeah. Okay, I understood your question. So the pumping is at a constant rate. Okay. I'm pumping at a constant rate for a long time. Okay. And when that happens, as the impact of pumping spreads farther and farther away from the pumping well, right? Initially, when I start pumping, the impact of pumping is only felt in the area right near the well, right? And then as time goes on, the impact of pumping expands and expands until it reaches the boundary, right? So as the gradient changes at the boundary, the stream flow that used to the base flow that previously used to go into this into the stream starts to reduce in quantity, right? When some of the water starts coming from stream flow, that means the amount of water coming from storage has to reduce, right? So that is what this is trying to indicate, that initially all the water is coming from the storage in the aquifer, and as time goes on, the component of water coming from storage in the aquifer keeps reducing. Okay, that slope of that line, don't worry about it. It's a qualitative picture. Okay, it reduces with time, and the amount of water coming from stream flow keeps increasing, right? And therefore, at large time t, you reach a state where the water coming from storage becomes almost zero, which is the definition of steady state. ds by dt equal to zero is steady state, right? At that time, all the water is coming from stream flow and no water is coming from change in storage in the aquifer. Okay, so the reason why it asymptotically goes to 0% is another way of saying that it takes a long time for steady state to be reached. Okay, now that's x-axis does not have any units right now. Okay, it just says time. It doesn't mention hours, days, whatever. Whether it is hours or days or weeks or months depends on the size of your watershed, depends on the rate of pumping, depends on the properties of the aquifer, like I was saying, right? That T by S, the hydraulic diffusivity, depends on the distance of the pumping well from the river. It depends on how much pumping is happening. It depends on for how long the pumping is happening, and it depends on the properties of the aquifer. Okay.
Yes, sir.
Okay.
Effect in storage in summer and monsoon time is different because base flow is increases in the monsoon time.
Good question. Now, the we are talking about this in the context of whatever the base flow is at a certain point of time, right? Now, base flow also is not going to remain constant as a function of time. Like you said, during summer, base flow will be at its lowest, and in the monsoon period or after the monsoon period, base flow will also increase with time, right? Whatever the base flow is, if I can capture some portion of it, if the pumping well is able to capture a portion of it, that results in stream flow depletion, whatever the stream flow may have been. It doesn't matter how much stream flow is going in. If if X amount of stream flow is going into the stream, if I'm able to capture 10% of that, that is stream flow depletion, right? Whatever that X is, that X will vary. In summer, it will be something. In winter, it will be something. In the middle of the monsoon, it will be something else. Okay, so this graph is just portraying the reduction. It's a percentage. It doesn't depend. It doesn't matter how much was going in. It of course is a function of time. Like what you have said is correct. But if you look at it as some kind of long-term steady state, right? If you look at it as a very long-term process, then net recharge is equal to net base flow. Whatever recharge goes into the aquifer under natural conditions, it will discharge into the river as stream flow, as base flow, right? And over that period, that time period, if I'm pumping out water from the aquifer, that water is not coming from the aquifer, it is actually coming from the stream. That is what this, I mean, it is coming from reduction in stream flow. Okay.
Thank you, sir.
Any other questions? No other questions?
No, sir, go ahead.
Okay. Okay. Thank you. This might be a via media solution for somebody else to have their microphone on so that they can, of course, anyway, fine. That's good. So let's move on. Now we will, so far we have been talking about it in a qualitative fashion. Now to quantify it, there have been n number of approaches being taken. The first one was from Thais in the 1940s, right? There was this simple uh, uh, function that he derived, right? Delta Q is the stream flow depletion divided by QW, which is the rate of pumping. The pumping well is pumping at a rate of QW at a distance of L from the stream nearby, and the stream flow depletion, which we're going to call delta Q, is delta Q divided by QW equal to this ERFC is called the complementary error function. Okay, it's called the complementary error function. Okay, I'm not going to get into what it is and so on and so forth. But it's basically you can use Excel. In Excel, you can use this function ERFC and put in some number into it. You'll get the value of the error complementary error function. Okay. Let's not worry about what it is. Let's just assume it's some mathematical function which gives you an answer. The error function, the argument of that error function is square root of SL square by 4TT. Now, this must remind you of the Thai solution. Remember the U that we used to have, U equal to R square S by 4TT. What was R? R was the distance from the pumping well at which you wanted to know the drawdown. Here, it's just been replaced with L. So it's uh, R square S or L square S by 4TT. Now, if you notice this, it has the hydraulic diffusivity, the ratio that we spoke about, T by S. Here I have S by T, which is inverse of my diffusivity. So the diffusivity, the property of the aquifer is embedded into this expression. Now you see there are one, two, three, four terms in this equation which determine how much delta Q is, right? Delta Q is determined by QW, how much water is being pumped. L, the distance from the stream where the pumping is happening. Small t, which is the duration, since how long are you pumping? At what time t are you wanting to find out uh, uh, the depletion? And the ratio T by S or S by T, whichever way you think of it, right? Hydraulic diffusivity is T by S. Here I have the inverse of the hydraulic diffusivity. So the depletion delta Q depends on what the pumping rate is, how much pumping is happening, at what distance the pumping is happening, for how much time the pumping is happening, and the aquifer properties. Right. So this is what I said earlier. So that is reflected in this quantitative expression. Right. So qualitatively, we knew these things, that delta Q depends on QW, L, small t, and T by S. Now I have an expression which explicitly tells me that these are the different factors on which delta Q depends on. Okay. So this is a simple setup. Now suppose I have a more complicated situation where I have the stream has a stream bed. Okay, so this is a stream bed. What is shown here adjacent to the stream is called the stream bed, and that stream bed has got some soil of slightly different properties, which has its own hydraulic conductivity K prime and its own thickness B prime. Right. So this distance of the pumping well is divided into L and another thickness B prime, which is the thickness of the sediments in the stream. Okay, so the aquifer is not connected directly to the stream. It is connected to the stream through a stream bed, and that stream bed has its own conductivity K prime and its own thickness B prime. Okay, so if that is the case, then you get a slightly more complicated looking expression for this delta Q. Delta Q by QW equal to, again, complementary error function, square root of SL square by 4TT, and then the correction is applied for the fact that I have the stream bed attached to the stream, which is kind of mediating the response of the stream. Right, so this correction is applied to it, and then all the expressions that are given there are just there to help us obtain this value of delta Q. Right, so now obviously this delta Q will also depend on K prime and B prime. Right, if B prime is very small, then or if K prime is close to K, then basically L is nothing, this capital L will be nothing but B prime, right? And so on and so forth, right? So it's just a way of explicitly incorporating the impact of the stream bed, which has a slightly different hydraulic conductivity and a thickness that can be applied into this correction for this expression for the stream flow depletion. Okay. All right, we'll move on. Okay, so this is just and I've just shown you two equations. There are n number of equations available. There are so many other expressions available. A lot of people have worked on this to derive a simple expression for estimating how much depletion will happen in a stream if so much pumping happens at such and such a distance, and so on and so forth. Okay, again, don't bother memorizing all these equations. It is just for information. Okay, you will not be expected to remember these equations. Okay. Now we'll talk about a few other environmental influences that can play a role in uh, uh, in impacting groundwater levels. Now, atmospheric pressure plays a role in the water levels in the wells. Okay, so now if the atmospheric pressure increases, it causes the water level in the well to decline a little bit. Okay, does that make sense? Does that make sense? You can think of it as the atmospheric pressure, when it increases, it just pushes the water level down. So that would result in a decline in water level. Okay. Now there is an interesting phenomenon that happens. I'll just try to draw a figure right here. Okay. Let's say I have a well in an unconfined aquifer. Sorry, a well in a confined aquifer. Wait a second. No, unconfined aquifer. Okay. Let us say this is my uh, unconfined aquifer, and I have some water table, and it's measuring the water table at this particular point. Okay. Suppose there's a rainfall event that happens here. Suppose some rainfall happens here. When you observe the water level in this well, okay, suppose I have a water level sensor in this particular well. What will happen is the water level, maybe it's like this, and then once the rainfall happens, suddenly it goes up. Okay, so this is the, let's say, the water level in the well. Let's say it's just responding like this, and then when the rainfall happens, suddenly you will see the water level go up drastically. Now, a lot of people, when they see this, they assume that this rainfall has entered into the ground and reached the water table and caused the water table to go up. Okay, when they see the sudden jump in the water table, uh, uh, in the water level in the well, people mistake this, assuming that this is happening because um, uh, the rainfall has resulted in recharge, which has gone in and started to raise the water level in the unconfined aquifer. But the time scale in which this happens, right? So if the rainfall happens for 1 hour, this water level increases very quickly, and then it actually starts to go back down. Okay, so this is as kind of a puzzling event that happens, and people are not sure why this happens. And then they figured out that what happens is, when I have a rainfall event, right? Uh, you know, water that percolates into the soil happens very, percolation, infiltration happens at a very slow rate. It might happen at the rate of centimeters per hour, right? It might not be able to move 10 feet or 20 feet within a few minutes, which is when you start seeing this response in the unconfined aquifer. But what is happening here is, when I have a sudden rainfall event, the water gets saturated at the top of the the soil profile. Okay, so the top of the soil gets saturated. Okay, close to the land surface, it gets saturated, which means the air molecules that are trapped between the water table and the land surface are trapped. They are no longer exposed to atmosphere. Understand what I'm saying? When a rainfall event happens, the top of the land surface gets saturated. The very top, maybe top few centimeters, let's say 4 or 5 centimeters, get saturated, which means the air molecules that are present in the unsaturated zone are no longer connected to the atmospheric pressure. Okay, because there is an in between the air molecules in the unsaturated zone and the atmosphere, I have a saturated thin layer of saturated soil. Okay, so the pressure in the air here becomes higher than, because it's now trapped. It's no longer uh, you know whatever, what do you call that, Boyle's law, PV equal to nRT, right? So the uh, uh, volume occupied by the air is reducing, the number of air molecules is the same, so the pressure actually increases, right? So when that pressure increases, the pressure at this point will no longer be atmospheric pressure, it will be slightly more than atmospheric pressure. So therefore the water level in the well will just go up. But it is not actual recharge happening which is causing the water level to rise. It is the fact that the air molecules trapped in the unsaturated zone, their pressure has increased, and therefore they are causing the water level to apparently rise up. Okay, it is not a real rise. The water level is not actually rising up. It is only because the water level sensor in the well is only measuring the pressure of water. Okay, it's not measuring water level. It is measuring the pressure of water. The water level does not rising. It's just the pressure that is rising. Okay, so this is an interesting phenomenon that a lot of people actually observe this and mistake it that recharge is happening so fast. Recharge does not happen within hours or within minutes. Okay, it usually takes days and weeks for recharge to happen. Okay, so atmospheric pressure actually plays a very important role in determining the water level in the in the groundwater. Okay. Okay, is there a question? Sir, so will there be a change in atmospheric pressure also? Wait a second. Will there be a change in atmospheric pressure also due to changing water levels due to groundwater pumping over large areas and affecting climatic processes? Okay. So the question is, will there be a change in atmospheric pressure also due to changing water levels due to groundwater pumping over large areas? I don't know if groundwater pumping can cause atmospheric pressure to change. Uh, I can't imagine how that would happen. Not sure. I can imagine that, Shaker. There might be some larger. Yeah, you have to be careful with the microphone in the room. Huh.
Because sir, I was visualizing this analogy with
If
if you
there's
feel
one second. If there's multiple
uh,
people there with microphones, just turn off except one microphone. Yeah, go ahead.
okay. Sir, if you fill a syringe half with air and half with water, then if we press the syringe, then it will affect the system.
Correct.
So I was just linking this analogy with this one.
Okay. Mm, syringe. See, syringe is a closed system, right? So now here, when I have a groundwater pumping and the atmosphere, it's the whole globe itself is one big closed system. I doubt pumping at a particular location can play that major a role in impacting atmospheric pressure. Okay, but maybe some atmospheric scientists might be able to throw better light on this. I'm not able to think about large scale groundwater pumping causing changes in atmospheric pressure. I'll think about it. I'll see if there's any literature available.
Yes, sir. Yes.
Yeah, thank you. Any other questions? Okay, let's move on. Oh, we are almost out of time. Thought I would finish this today. Okay, let's quickly go through urbanization. You can easily imagine the impact of urbanization on groundwater levels. What is the major impact of urbanization? I have concretization of surfaces, which reduces recharge into the aquifer, and therefore it's going to reduce the water levels in urban areas. Okay, it reduces recharge basically. Okay, external loads. Now this is very interesting. I'm going to show a picture of what happens when a train uh, 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 comes and stops at a particular point, and the impact of the train coming and stopping and starting actually plays a role in affecting the water levels in the wells nearby. Okay, now this is again, it's 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 a, it's not that the water level is actually rising. It is because of it's connected back to this pressure. Remember, we spoke about uh, in a confined aquifer, there is the combination of the intergranular stress in the soil matrix and the pressure of water, right? So when this external load, when a train arrives at a particular location, it is increasing the total stress acting on that confined aquifer, right? Now that has to be compensated with either the intergranular soil matrix has got to, it is getting compressed, right? When that train arrives, it is compressing that matrix, and then it results in a slight increase in the pressure of the water, which reflects as a rise in the water level. And then it's not that the water level is actually rising by that much. It is just the pressure of the water is increasing, which translates into a rise in the water level. And then when the train starts again, that load is released, then the water level actually drops. There's a decline in the pressure. So you can see at these 2 points, when the train stops, there's an increase in the water level. And then when the train starts, there's a sudden decline, and then it starts to again uh, go back to its original kind of trend that was going down. In any case, there was a trend in the groundwater level. This dashed line is showing the trend in the groundwater level and how the arrival of a train and the departure of a train actually impacts that trend. Okay, so the water level goes up and then comes down and then actually stabilizes, and the train is stationary. And then when the train starts again, that load is released off the aquifer. It's a dynamic load, of course, and so therefore there's a dynamic response of the groundwater level, assuming that there are no other stresses in this short 15-20 minute period. If you see the x-axis, it's about between minute 8 to minute what is that, 18 or 19. Okay, so in that 10-12 minute period, this whole scene is evolving, and you can see uh, during those 10 minutes, it's unlikely that anything else changed. The only thing that was happening there was the arrival and the departure of the train and how that impacts the water levels in this particular region. Okay, let's keep moving on. I'll try to finish this, just a couple more points. Land subsidence, we've already spoken about it. When there's excessive pumping, this the compression of the aquifer results in land subsidence. We have already spoken about this earlier. And then, of course, global warming and climate change, the impacts of these two factors, climate change or global warming on groundwater, is actually an evolving topic of interest. A lot of people are looking at this and trying to understand how global warming and climate change are going to play a massive role in impacting water levels at the global scale. Okay, of course, there'll be local impacts, but there'll also be global impacts across the world. Okay, just one final topic. Again, you don't have to memorize this. The ocean tides also play a role in impacting the water levels in an aquifer that is attached to the ocean. So the aquifer, if it is connected to the ocean, the response of the aquifer in due to the tides in the ocean can be modeled in this kind of a simple 1D problem: dou square h by dou x square. Uh, that's the response of the head in the confined aquifer in the x direction is a function of it's a function of time. So it's s by t times dou h by dou t, and the boundary conditions here will be h naught sine omega t. That's the ocean tides going up and down. The omega refers to the you know the time period of the tide, and then h naught is the amplitude of the tide, and so on, right? Anyway, so then the response is that you have an exponentially decaying solution with a time lag, the sinusoidal variability with a time lag. So the sine, what is that? Sine omega t. There's sine omega t, and then there is a time lag also attached to the. I'll explain this maybe in the next class because we are kind of running short of time. I'll explain this and then we'll move on to the next topic. Okay, we'll discuss this briefly and then move on to the next topic in the next lecture. Okay. Well, anyway, we'll meet on Tuesday. Take care, everybody. I know the quiz 2 is right now in progress, so all the best for your quizzes. And we will meet on Tuesday. See you all. Bye bye.